Hi, I'm Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is Irrational. We'll look at some of the surprising facts about the irrational number e. Irrational means that e cannot be written as a ratio of integers, and also that its decimal representation does not repeat forever. The value of e starts with 2.71828, and that's as far as you would normally want to go, because the next four digits repeat, 1828, which makes it hard to claim that the digits do not repeat. If you go to that second 1828, you want to go a little further, get the 4590, and break up the pattern. It has a letter name E because of its lack of fraction or finite decimal representation and due to its importance in applications. We'll look at some of those applications here. The use of E goes way back in time, though not as far back as the more famous irrational number pi. In 1683, Jacob Bernoulli found E as the answer to a question about compound interest. Suppose you have $1 and you can earn 100% interest. Don't you wish? If interest is compounded, calculated once per year, you have original $1 plus your 100% interest, another $1, $2 at the end of a year. Now, compounding twice means that you get 100 over 2, 50% twice. First, you have your dollar plus half of that, so $1.50. Then $1.50 plus half of that gets you to $2.25 after 1 year. Before taking the next step, notice that we can simplify that calculation. If you add 50%, you have 150%. So you can calculate these as 1.5, 150% of 1, and then 1.5 times 1.5, giving you the same 2.25. Or you could just say it 1.5 squared equals $2.25. What if we compound 10 times per year? Well, you get 100 divided by 10, 10%, 10 times. Adding 10% means you have 1 plus 0.1, 1.1, 110% of what you started with. So doing this 10 times puts you at 1.1 to the 10th, which is 2.5937 and other digits. $2.59. You're finishing with more money because you're getting interest on the interest. Is there any limit to how much you can get in a year? If you compound n times, you get 100% divided by n, or 1 over n added on n times, which makes 1 plus 1 over n to the n, and this does not go to infinity, instead settling down at a limit as n gets larger, written as limit as n goes to infinity, 1 plus 1 over n to the n, 2.71828, which you'll recognize as the beginning of E. A remarkable fact lets us easily compute other percentages. If we're getting a more realistic 7%, then continuous compounding for a year gives us the limit of 1 plus 0.07, 7%, divided by n to the n, and that's the same as e to the 0.07. Amazing. So the function e to the x can be the percentage, gives us an easy way to find the amount of money resulting from continuous compounding. For similar reasons, e to the x also helps us compute the increase in population of a group growing at a constant rate. The overused phrase exponential increase refers to the rapid increase of this function. Also, e to the negative x gives us the size of a quantity that is decreasing at a constant rate. So, studies of population change, ecology, chemical reactions, nuclear energy, and many more areas use e to the x for basic calculations. Since these applications rely on calculus, let's just summarize by saying that e to the x is the most important function studied in calculus and subsequent courses. So we have a definition for e and a sampling of important applications. There's much more. It turns out that e is also equal to the summation as n goes to 1 to infinity of 1 over n factorial, where that exclamation point means factorial function. As an example, 4 factorial is 4 times 3 times 2 times 1. As with the compound interest definition, the importance of e in this context comes from the more general formula, e to the x equals the summation n goes to 1 to infinity, x to the n over n factorial. From this, we get an essential and surprising connection to the trig functions sine and cosine that gives meaning to complex numbers in many applications. Recall that complex numbers reference the imaginary number I equal to the square root of -1. So if I is the square root of -1, I squared is -1, I cubed would be -I, I to the fourth is 1, and so on. Replacing x in the e to the x formula with ix then leads to the equation e to the ix equals cosine of x plus I sine of x. The same function that can give exponential growth and exponential decay can also be used to describe oscillations in electronics and mechanics. Like its fellow irrational number pi, E also shows up in the solution of a large number of diverse problems. The following is called a derangement and can be stated in many ways. Suppose you are having a dinner party and have carefully planned a seating arrangement. Name cards are placed at the proper places, but the cards are ignored as people sit down at random places. What is the probability that nobody sits where you intended them to? If there are n people, the answer is 1 over 2 minus 1 over 3 factorial plus 1 over 4 factorial, and so on out to 1 over n factorial. For 4 people, this equals 0.375. What if the party has a huge number of people? Is the answer 0 because somebody will surely stumble into the right seat? Using the summation definition of E, you can show that the more people there are, the closer the answer gets to e to the -1, which is 1 over e, 0.3678. It's surprising to me that there's always a more than 1/3 chance that nobody gets the right seat. In general, probability questions often require calculations involving e. The reason becomes clear if you graph the function e to the -x squared. Yep, that's the bell-shaped curve associated with the normal distribution. You need to be able to compute areas under this curve to compute probabilities for random variables that are normally distributed. There are also many odd instances of e in calculations. Does the calculation x to the x to the x to the x not turtles all the way down, but x is all the way up? Does that make sense? If x equals 2, you would clearly get 2 to the 2 to the 2 to the 2. You'd get infinity as an answer. But there are x's for which the infinite process does give a finite value. The smallest such x is 1 over e to the e, and the largest such x is e to the 1 over e. Weird, but nicely symmetric in a way. Continued fractions were a popular way to represent numbers in the 1700s. The great Leonard Euler, who gave e its name, found a wonderfully patterned representation for e. It's a typesetting nightmare, but continue the sequence 1 over 1 minus a half, then replace the 2 with 2 minus a third, then replace the 3 with 3 minus 2 fourths, replace the 4 with 4 minus 3 fifths, and so on. At each stage, the last denominator is n, which is replaced at the next stage with n minus 1 over n plus 1. These fractions compute to 2, 5 over 2, 2.5, 8 over 3, 2.67, 65 over 24, 2.7083, and the sequence converges to e. However, e is also part of a simple equation that has been called the most beautiful equation in mathematics. To start, notice that with x equals pi, the equation e to the ix equals cosine x plus I sine x becomes e to the I pi equals cosine pi plus I sine pi. Well, cosine of pi is -1, sine of pi is 0, so that's just -1. Add 1 over to the left, it follows that e to the I pi plus 1 equals 0, an equation simply relating 5 fundamental numbers of mathematics, e, I, pi, 1, 0. And that's where this episode stops, with what has been called the most beautiful equation in mathematics.